Okay.
Hi, I'm back.
Okay.
Thank you.
Welcome back. Can you share the screen?
Yeah, go ahead now. You see this?
Yes. Yes. So, okay. So
Good.
for the last talk, Roberto Trotta, Stratified Learning, a general purpose method for learning under covariate shift with applications to observational cosmology. So please, you have 12 minutes.
Thank you. Thank you to the organizers for the opportunity and also for going fully hybrid with this. I do think this is the future format for conferences in our field. I want to pick up this thread on domain adaptation that Alexandra was talking about with a specific case, domain adaptation technique that we've mutated from causal inference called stratified learning, which is statistically principled, very simple, yet we think quite powerful, at least on the cases that we tried it on, and generally applicable. This is work done in collaboration with David Van Dyke at Imperial, David Stenning at Simon Fraser, but mostly work done by Max Autenried, an Imperial Statistics PhD student. So the fundamental problem that we're trying to address is that of non-representative training sets. And it's well known that machine learning classifiers or machine learning supervised systems in general, which are trained on non-representative training sets, generalize poorly. We see lots of examples in applications, many of which are generalized poorly because of biased training sets. We've seen examples in Google Photos in 2015 when Black people were misclassified as gorillas. We've seen examples in terms of the facial recognition accuracy of commercially available software, which is much better at classifying white male faces than darker skinned female faces. And in cosmology, we know that incorrect classification of supernova type 1As, for example, will introduce biases in cosmological parameter inference from photometric data sets. And the same is true in terms of incorrect photo Z estimation from non-representative spectroscopic training samples. And so this is a widespread problem that it's important to be able to address. Now, when we talk about supernova type 1A, which is the kind of cosmological example I have in mind, although many others are relevant and possible, we now have about 1,000 or so spectroscopically confirmed 1As. Here's a recent data set. And the point is that while we can do dark energy constraints and other cosmological parameter constraints from this data set, those are spectroscopically confirmed type 1As. Which is a great data set to do cosmology with because we know those are 1As. But in going forward in the future, we will have many more supernova candidates and many more in such numbers indeed that with the Rubin Observatory, for example, we won't be able to have spectroscopically confirmed typing of these supernovae, and therefore we'll have to make do with photometric data only for the vast majority of these very large numbers of supernovae that are expected in the future. So if you want to exploit the power of this data, we need to have machine learning methods that will, in a supervised manner, learn the typing of the 1As from a much smaller and non-representative training data set. So this brings us to the problem, which is that we want to classify type 1As versus non-1As reliably and efficiently from light curve data alone under the problem of covariate shift, the fact that the spectroscopic training set is non-representative. So covariate shift is a particular case of domain adaptation, which specifically arises when we have a feature space, X, and a label space. This could be a discrete classification case with K classes, or it could be a regression case with K-dependent variables. In the case that I have in mind, again, the feature space is the light curve data, and the label space is simply binary classification type 1A or not. In general, in this supervised learning task, we have a number of labeled samples, for which we know the covariates or the features, XS. We also know the labels from the source domain. That's our spectroscopic training set. And then we have a potentially much larger set of unlabeled samples from the target domain, for which we have only photometric light curves. We don't have the labels. We only have the covariates or the features, Xi's. And the task is to predict, in this case, the classification variable. And the case that I'm interested in, which is very common in astronomy and cosmology, is that of covariate shift. That's the case where the conditional distribution of the labels conditional on the covariates, X, is the same between the source and the target domain, but the distribution of covariates is different between the source and the target. In other words, the training set is non-representative of the test set. So on the left side, you see an example here showing two-dimensional feature space for type 1a supernovae. What we would like to have is a case where we have a representative set color-coded here in orange and blue of 1As and non-1As with respect to the test set, which is what we see in this picture. This is not what we typically have. What we have is something like this, where the spectroscopic training sample is a non-representative of the target set in gray here. We don't see higher redshift and fainter supernovae all that much in the spectroscopic training sample because they're not followed up. But also there is an over propensity to follow up 1As spectroscopically or tentative 1As, and therefore we see many more orange dots here. We don't have a representative training sample. So if we train a classifier on this training set, its generalization to the test set will be poor. So our approach is based on a trick that's been used for a number of years in causal inference, namely propensity score classification, stratification. This improves on previous work that we did with David Van Dyke and another master student, which was called Staccato. And the idea is very, very simple. We look at propensity scores, which simply put, a propensity score is the probability for a certain object I to be classified or selected into the source domain. So in other words, the probability that a given supernova, given its covariates xi, is observed spectroscopically and followed up and typed spectroscopically. So let's say that we have a model here for this probability. It would be as simple as logistic regression. In fact, we use logistic regression and it works perfectly fine. And the idea of stratlearn is simply to subdivide, that's to say stratify, both the target and source data in a number of subgroups according to quantiles of the distribution of the propensity scores. And then we perform supervised learning of any kind, whatever you want to use, be it support vector machines or neural networks or any model that you have, but you do this learning inside each stratum separately. This is what we call the stratified learner. And why do we think this is a good idea? Because there is a theorem by Rosenbaum and Rubin from the 80s that says that propensity scores are approximate balancing scores. So if you condition on the propensity scores, that's to say approximately within each of the strata that are defined by the stratification in propensity score partitioning, the covariates are approximately balanced between the source here and the target. And therefore, under the covariate shift assumption, because the conditional distributions are the same, the joint distribution is going to be approximately the same. So in other words, within the strata, we have almost representative training sets, and therefore the covariance shift problem goes away. And so this is an example applied to supernova data, where we see here at the top the stratification done in a two-dimensional covariate space, a proxy for brightness, pattern brightness, and redshift. You can see very clearly that the 5 strata here from the top to the bottom, those are decreasing probabilities of being in the training set. So we can stratify both the source and the target according to this prescription. This was an early example using Staccato on simulated data. And down here you see the stratlearn approach, which uses the entirety of the light curve data through diffusion mapping and including 102 covariates. You see the boundaries now become a little bit more blurred because we have 100 covariates that are not shown in this picture, but still you can see the stratification broadly follows the same pattern. And what we find is that inside each stratum, because the imbalance has been redressed, the source data is approximately representative, and therefore our classification is much improved. Indeed, if we look at the proportions of 1As to non-1As between source and target, we can see that within the first 2 strata, the topmost strata, we achieve perfect balancing between the target and the source, which means that the theorem indeed works perfectly well in these 2 examples, in these 2 strata. In higher strata, this is not quite the case because, of course, we have very little number of source points in the higher, less observed strata. An important thing to remember is that the theorem that underlies this idea is only valid if all potential confounding covariates That's to say the things the classification in this case could depend on are included in the propensity score estimation. And that's why in StrataLearn, we throw all of the data at the propensity score model so that we have the entire light curve included into the model. So once you apply it on simulated data, you can see that it works very well. It achieves an AUC for this simulated photometric classification challenge data of 0.958, which is close to what you would get from an unbiased gold standard training set without any augmentation. There are very strong, very good classifiers out there. For example, Avocado that works based on augmentation. We don't use augmentation at all because augmentation obviously is a problem-dependent tool. And this is better than anything else that has been used before on the same data set. I just also want to say this is not limited to classification. It can do regression as well. We also tried it on PhotoZ conditional density estimation from SDSS data, where again you see an example of very strong covariate shift. The R magnitude of the spectroscopic training sample and the PhotoZ sample shows a strong shift in distribution. And again, we see performance that is better than anything else that has been tried before. And it's particularly advantageous in high dimensions when you have a lot of noisy covariates. So you don't need to do dimensionality reduction. You just do it directly in the high D parameter space. The actual performance improvement differentially to other methods is better in high dimensions. And so in conclusion, covariate shift is an important phenomenon that occurs everywhere in supervised learning, particularly for dark energy research and constraints. It will be important to address for the next generation of large supernova type 1a data. Proposed StrataLearn as a method to stratify source and target domain according to propensity scores, very general, very problem independent, and very powerful. Within the strata, the source and target domain are better balanced. And that means that you observed improved performance in regression and classification tasks compared to best-in-class alternatives. And I'll leave you with this, and also with the thought that there is a postdoc opening in my new group at CISA. So if you're interested in machine learning across Astro and you're looking for a postdoc, please do get in touch. The deadline is November the 11th. Thank you.
Thank you very much, Roberto. Any questions? The speaker. Start to be the end of the day. I saw in Slack, but Angus answered the question apparently. So, which was actually, yeah, it was about like modeling, this stratified learning is like a way to model highly complex selection function. Actually, maybe you could elaborate a little bit more on that. So can you transfer this to other fields?
As a way to it's a way to mitigate against the effects of highly complex selection functions. You still need to be able to model what's happening to the data in order to know what the propensity score will look like. But certainly if you have selection effects at work, you will want to be able to mitigate against that. And therefore, that's a method that could help doing that.
So I guess that you're preparing for LSST or...
Indeed, indeed.
Another question? But I think that otherwise we're going to close the session. So thank you very much. And,
thank you.
And that will be the end of the afternoon session. So a round of applause for all the competitive talks of this afternoon. So we have now the debates at 6, so in 20 minutes. Okay, let's say that we make 25 minutes to give a bit of breath. And so reconvene at 6:05.